Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have completed 12 chapters and it's a good idea to take stock of where we are in the course. So we motivated the course by pointing out the puzzles posed by phase transitions, the idea of universality and universality classes. We decided to look at microscopic models and we pointed out that the notion of symmetry, the notion of scales are very important in constructing these models. And also we pointed out that if you want to get distinct phases, you have to have some kind of interaction between the degrees of freedom. We were motivated to characterize phases using symmetry, primarily motivated by experiments. And then we introduced the notion of the order parameter. We looked at microscopic models and learned how to analyze them using some series expansions using some small parameter. We then went on to look at very special models which could be solved exactly, and in the process we also learned about the idea of duality, that the physics can be described in different models and those models could be related by duality. So up until that point in the course we had discussed classical systems, then we went on to do quantum systems and we discovered something very interesting which says that a quantum system in d dimensions is sort of equivalent to a classical system in d+1 dimensions, particularly in equilibrium. We then looked at non-perturbative approximate methods, so particularly mean field theory, which is very useful in determining overall phase diagrams of given models. And we then realized that to describe things in general and to analyze critical phenomena, etc., it's useful to adopt a phenomenological approach. And we went on to study the Ginzburg-Landau model. Landau's approach was generalized by Ginzburg and Landau-Ginzburg theories were used. And we from there inferred a variety of very interesting things, namely the idea of upper and lower critical dimensions, the notion of Mermin-Wagner theorem, which states that you cannot break a continuous symmetry in systems with short range interactions in spatial dimensions 2 and less at finite temperature. So this is the point where we realize that our simple approaches using saddle point approximation and fluctuations treating Gaussian, etc., are not able to explain the universality and critical phenomena. In fact, they probably over explained it in a sense that all the exponents turned out to be the same, which we certainly don't find is true. And this was then addressed by introduction of the scaling hypothesis, which said phenomenologically that the singular part of the free energy near a critical point will be some generalized homogeneous function of the variables. And while the scaling hypothesis was successful in explaining scaling laws, it's not entirely clear how this generalized homogeneous function arises. And to address that question, we discussed the renormalization group as formulated by Wilson. And the central idea of the renormalization group starts from the observation that at a critical point, systems have a new emergent symmetry, an arena symmetry, which we call scale invariance. And once you have this symmetry, using that notion of that symmetry, you can develop a lot. And Wilson actually formulated the renormalization group using that. He found a way to do the scale transformation, and in the process of doing scale transformation, what he was able to point out is how the low energy degrees of freedom, long wavelength modes of the system, how they are affected by the short wavelength modes, and he showed what kind of information can go from the short wavelengths to long wavelength in a very nice way. And not only was it able to explain all the different phenomena of critical physics based on qualitative arguments, it was also able to provide a tool to compute. We computed the critical exponents and so on. So in a sense, the last chapter essentially solves the problem that we set out as a goal for the course. but there are still many things that we have to figure out, in the sense that we would like to sort of complete the story. In particular, what we will do today is we will study what is called as a nonlinear sigma model. So this is particularly useful when you want to study things near 2 dimensions, as you will see. Nonlinear sigma models are also useful from another perspective, which I will discuss in the next slide. But to do that, I have to point out that when we discuss this ON symmetry model, a Landau-Ginzburg model, we did not assume any symmetry breaking, which certainly will happen if if you go low enough temperatures, etc. So we analyze the problem on the unsymmetry broken side, but we will certainly get the same correct critical exponents because of the nature of the critical phenomena, in the sense that the exponents are same on both sides. The amplitude ratios will take care of the differences on the symmetry broken and the non-symmetric and the symmetric side. So with that, it's interesting to ask, like, how would you address the problem if you did indeed break some symmetry? Okay, so I will motivate this discussion by pointing out that when you go to lower dimensions, as we have seen many times, particularly in the last section of our discussion of phenomenological theories, we saw that fluctuations are very, very strong in lower dimensions. In fact, they are so strong that they can actually destroy any ordered state if you have continuous symmetry. So a continuous symmetry cannot occur at a finite temperature in a classical system in spatial dimension 2 and less, and this is the Mermin-Wagner theorem. So whenever you break a continuous symmetry, we saw that you get 2 types of excitations. The first excitations are gapped, and these are what we call as the amplitude modes. So if you think of breaking symmetry as developing an order parameter, then you can think of the expectation value of this field that we have as the order parameter, and you can think of this as some very slowly varying field in space, and this order parameter field, it can have amplitude fluctuations, namely the size of the order parameter changes, as far as it can have directional fluctuations in the ON space, and this local order parameter, if the amplitude changes, will produce a gapped excitation. So this is called as the Higgs mode. Similarly, you can have excitations in which the amplitude of the order parameter or of the field does not change, and these are what we call as Goldstone modes, and we discussed at length that these will be gapless, they will not have any gap. So the natural question to ask is, if I have gapped excitations, I can integrate them out, just like we integrated the highly fluctuating modes. You could, in the same vein, you could actually integrate out the gap modes, and you will end up getting an effective action for these Goldstone modes. So naturally, if I describe the Goldstone mode by some field, the magnitude of that field cannot change, because the magnitude is not supposed to be changing the Goldstone mode, because the Goldstone mode has only the you are sort of moving on the unit surface of some order parameter space, and therefore you will be you will not change the magnitude of that vector. So if you want to describe the low energy physics solely by Goldstone modes, it is very natural to introduce a model where the field is not the ON field with any arbitrary component of vectors, etc., but to describe the state or the configuration of the system using a field which is a unit vector. It is a unit vector in the ON space. That means it is an n component unit vector. So n dot n will be always 1, and we can write down such a model, and this model is called as the nonlinear sigma model. So sigma model has historical connection to quantum field theory of high energy physics, etc. Nonlinear is used because of this constraint. So we will see in the next slide that when we write down this theory, you will see that it will appear very simple. So, the whole complication is in actually introduced in resolving this constraint, and this is what will give rise to all the interesting non-linearities in the system, and that is why it is called as a non-linear sigma model. Okay. So, with that motivation for doing nonlinear sigma or discussing nonlinear sigma models, let me introduce the model itself. So, as I just mentioned, you define a model in this continuum arena where the fields are these unit vectors in the ON space. So, there are n components and everywhere their magnitude is 1. Okay. So, the configuration of the field will be some function which is a function of unit vectors, it's unit vectors attached to every point in space, and what I am giving as the action is I look at the gradients of n. So, what I am asking is the n here almost same as the n in the neighboring site, in the neighboring point. Naturally, if I have a broken symmetry state and I do not want to have any fluctuations and I really want to be in the ground state, then of course all these n's will be same everywhere. But if they are not, having a difference in the direction of n at different places nearby will cost you some energy. That energy goes as gradient of n. So, this gradient is the spatial gradient and n is a vector in this ON space. So, the meaning of this is precisely what we have done in the Ginzburg-Landau theory itself. So, di is a spatial derivative, alpha is the index in the ON space. So, it is an ON scalar as well as a spatial scalar. So, this is the very simple, very you might say commonsensical form of the interaction, and it looks like a Gaussian theory. I emphasize it looks like, it is not, right, and there is a coupling constant which we call Gp, and as we have been following in the course, P means it may have some physical dimensions, it is not a dimensionless number. We will soon see what it contains. So, this is the model. So, how do we do the partition function? The partition function is, of course, you just do the functional integral over all possible configurations of your n field which are unit vectors. But now you say I can't choose arbitrary n fields, I have to choose n fields which are unit magnitude everywhere. So, this integral, path integral is integrating only on a space of functions which are vector valued functions, n component vector valued functions which are unit vectors everywhere. That is the difficulty. To do this integral on such configurations is what is the difficulty, and that is why we say it is non-linear. So, this looks like a linear quadratic theory, which means you may think that, oh, I can just integrate it like Gaussian. You cannot, because this the difficulty is in actually maintaining this constraint. Okay, let me make a couple of remarks. So, as always, our theory has an ultraviolet cutoff in momentum space or wave vector space, and we call it lambda. So, the theory obviously has a global ON symmetry. So, what you can do is you can take, if R is some ON by ON n by n orthogonal matrix, which means it is an element of ON, then if I simply act R on n, I will get a new unit vector, and you can see that will leave this action invariant, which means this global R is ON rotation is a symmetry, fairly straightforward. So, as I pointed out, although this looks like a Gaussian theory, the nonlinearity arises from this constraint. Okay, so because we have chosen this n to be a unit vector, this theory is completely constrained as far as the dimension of this field goes. The dimension of the field is 1, it cannot have any physical dimensions. So, it goes as L to the power 0 or even lambda to the power 0. In fact, the fact that it is unit vector is going to be our renormalization condition. Okay, so this is exactly the condition that we will use when we do renormalization group. Okay, now the only thing remaining is to discuss the dimensions of this physical coupling constant Gp. And you can see simply by power counting here, because the action has to be dimensionless, you will see that Gp's dimensions is length to the power d minus 2. You see there is length to the power d minus 2 in the numerator, and therefore you see Gp has to have length to the power d minus 2. That means Gp's dimension in momentum language is 2 minus d. In other words, Gp can be written as a dimensionless coupling constant little g times lambda to the power 2 minus d. Okay. So, G is the dimensionless coupling constant. Okay, so we have defined the model now. So, let us try to see what we can sort of conclude by just general discussion. So, the first thing that I would like to point out is that this Gp has a very natural meaning of a temperature. Why is that? Because if I were to think of this as some energy, so that will be like e to the minus some energy by T. So the action will have exactly that structure. In fact, the dimensionless coupling constant can be thought of as a dimensionless temperature. So naturally you can ask, what is the state at G equal to 0? So the state at G equal to 0 has to be such that I cannot have any gradient in n, because any gradient in n, so if the n changes from point to point in space, there will be a gradient and it will cost me energy. So I cannot have any gradient in n. That means that n has to be fixed unit vector everywhere, which let us call it as n0. And now you see the state has broken symmetry. So this is my statement that I started off with. If I break the symmetry, I can sort of characterize it by the sigma model, because I am going to only work with gapless modes. Okay, and this is the idea. And so at 0 temperature, you will see that the state that is picked out will have uniform n everywhere in space, and that state breaks symmetry. So now suppose we do not worry about the thermodynamics. We ask, okay, so I give you the system and it's broken the symmetry, what is the excitation spectrum above it? So it's very easy for you to see that it is actually gapless. This is because I can deform, if I take a very long system and I can deform from n somewhere here to n slightly tilted there in a very slow fashion, I can make it as slow as I want, and therefore I can reduce the energy to however small I want, and in the thermodynamic limit I can make it 0. So these are examples that we have worked out very early on in the course about the XY model and so on. So these gapless modes of this theory are the Goldstone modes, naturally, right. So you are even guaranteed that they exist. So the very important question to ask is, what is the fate of this broken symmetry state when temperature is positive, that is G is greater than 0? So you might wonder, okay, why should we worry about this? Because we have broken a state and we have broken symmetry at 0 temperature, so I should be symmetry broken at finite temperature. That's certainly not true. You know this very well by now, because if you look at the one dimensional Ising model, the 0 temperature has some ferromagnetic state, but in the thermodynamic limit, any finite temperature will kill that ferromagnetic order. So this is exactly the question similar to that we are asking. The 0 temperature broken symmetry state, does that survive at finite temperatures? So what is a natural question to do? By now we know how to analyze this at the simplest level. We simply look at the tree level renormalization group of the G. So we know tree level renormalization group will be given by the dimension of G, right, momentum dimension of G. So we see that dg by dl is 2 minus d times g. So now we see something absolutely spectacular, which is that if you are in one dimension, g is irrelevant. What that means is, in one dimension you cannot have a stable broken symmetry state with this continuous symmetry in d equal to 1 at finite temperature, because it's a relevant operator. So the RG flow will look exactly like the 1D Ising model. I have the 0 temperature, and on 0 the G, which is now has the meaning of temperature, is a relevant operator, and it will flow away, which means that I will develop a correlation length, and it will, as I do scaling, it will become smaller and smaller, and it will look boring paramagnetic kind of state. Okay, so this is very reassuring because now we know it's sort of agreeing with what we already know. But now comes an interesting thing. If I look at d equal to 2, I am finding that G is marginal. That means at tree level, increasing temperature quote unquote does nothing to my state in terms of the scaling properties. That is what it means. So this does not really give you any insight at this level of renormalization group. So probably we have to do more calculations, go beyond tree level to get some insight into this. Okay, now comes the most interesting thing. So if I am in d greater than 2, now you see this number is negative. So what am I finding? I am finding that this operator is irrelevant at G equal to 0. This is telling me that I can definitely break a symmetry, ON symmetry for any n in dimensions greater than 2, and it will be a stable phase in the sense that there is only an irrelevant symmetry preserving operator that is arriving at this fixed point. So this is telling me that ON symmetric models will have a broken symmetry phase in 3 dimensions. So you can see that the renormalization group idea is really powerful in the sense that without solving anything, we are able to conclude these sort of things. Okay. Okay. Now what happens in the other limit, that is G equal to infinity? There what happens is the partition function, any kind of configuration of n which are unit vectors, it can be however fluctuating, will produce, is equally likely because G has gone to infinity, all states have, if you wish, equal probability. So this is like infinite temperature, and so every site, if you wish, or every point in space, if you wish, has an n which is doing whatever it wants. So this is the paramagnetic state, which sort of uncoupled unit vectors sort of hanging around in space. That is the state at the infinite temperature. So you can see that starting from this model, armed with the knowledge of renormalization group, we can make many useful conclusions without doing any serious calculations. But the natural question to ask is, okay, what is the story in d equal to 2? And okay, we know that there is a stable phase at 0 temperature in d greater than or equal to 2, in d greater than 2 strictly. Can I find for example, a critical point, that is, if I keep increasing temperature, I have to go to some paramagnetic phase like we find here. Can I find that critical point? So these are some very natural questions that we can ask, and we will ask these questions to the nonlinear sigma 1. So I have to do a little bit more than tree level renormalization group, and I am going to do the Wilson's method. So I am going to introduce the same integrate, rescale, renormalize mantra, and here is what we are going to do. We are going to follow an approach by Polyakov, and what we are going to do is we are going to develop a scheme to implement this RS, Wilson's renormalization group transformation, for a scale factor s greater than 1. So the natural question is the following: I have to take the n fields that I have, and I am going to break them up into long wavelength modes, which we will call capital sigma of x, containing wave vectors less than or equal to lambda by s, and short wavelength fluctuations of wave vectors lambda s by s. Okay, there is a mod, there is a line missing here, we will fix that. So it is lambda by s less than mod k less than or equal to lambda. So in that sliver of of the momentum space, which is which is very close to the cutoff momentum, there is a small shell which we have these short wavelength fluctuations. Okay, so here is where we will slightly depart from what we did in the usual Wilson's way of doing it. So we know that after we rescale and renormalize, these new fields have to become unit vectors. So if we simply take the Fourier transform n and just take all the wave vectors inside the lambda by s, you will not get a unit vector. So this is the kind of parameterization that was introduced by Polyakov to handle both the renormalization condition and the fact that the original vector is also a unit vector. Polyakov himself in his paper attributes this way of parameterizing the field n of x to Berezinskii and Blank. So what is the idea? The idea is sigma of x is a field which is a unit vector, and if I now write it as sigma of x plus something else, then if I simply write it like this, then I will not be able to make n of x into a unit vector. So what I do is I introduce a fluctuation which is short wavelength fluctuations, which is psi of x, and what I do is I normalize this n of x, which is a unit vector, mind you, by the square root of 1 minus psi dot psi, and of course I will keep the psi of x and sigma of x orthogonal to each other. And this, when I square up, I will find that the square of this vector, which I am defining as n of x is a unit vector. So you will see that this will square to 1. So this is a very clever way of taking into account the slow and fast modes in such a way that the nonlinear constraint is respected. Okay, what do we do now? Now the trick is the following. We are going to integrate out psi of x. So I will stick this into the action. I will integrate out psi of x and find an effective action for sigma of x. Very, very standard thing we are doing in a normalization group, but you will see that performing this calculation here requires some skill and maybe even some creativity. Okay. So what Polyakov does in his paper is he introduces a local basis in the ON. It's a local basis of the ON space. Local means what? The ON basis vectors, they are chosen differently in different points in space. So when I wrote originally that n of alpha, the basis vectors at every point in space were the same for the ON vectors. But what Polyakov does is he chooses a different basis for the ON space in different places. You will see why that is how that will help us. So the way the bookkeeping is done is he is going to label the unit vectors of the ON space as E0, this convention, 1, 2 all the way up to n minus 1. So this A is here, the letter A here stands for going from 1 to n minus 1, the other n minus 1 components. And what is this E0? E0x at the point x is along the direction of sigma of x. This is the starting point. Then there are n minus 1 other unit vectors which you can choose. In fact, you have a lot of freedom to choose that. So you will see that E0 of x dot EA is 0 and EA dot EB is 0 and the EB is delta IB, which means that unless they are the same, you will get 0. Right, and so these are the conditions. So he chooses this basis. Now sigma of x is simply E0 of x, and because sigma x and psi x are orthogonal, psi of x has only components along EA, A going from 1 to n minus 1. It has no component along E0, which is the sigma vector. So this is the parameterization. All right. So now why are we doing this? Because we want to take this information, put it in this n of x and take derivative with respect to space and square that derivative. So it's a bit of algebra, and it's greatly simplified if you use this local basis which is changing from place to place. Okay. So like I said, we need a little bit more technical things here. Because this E0 dot E0 is identity, or 1 I should say, the number 1 at every point in space, if I take a spatial derivative of this, it will turn out to be 0. Okay, so there is an error here, I think. This turns out to be 0. E0 dot gradient of E0 is 0, of course, that's because this is a constant. Because E0 dot this quantity is 0, it means that at every point in space, the derivative of E0 has only components along EA, A going from 1 to n minus 1 at that point. So we can introduce some coefficients, and you can see that the notation A is used, and if you are familiar with quantum physics, etc., A is typically reserved for vector potentials, etc. So yes, there is some gauge field and all that we can formulate, but we will not go there. So this A0 IA is the component of the derivative along I direction of E0 along the EA basis vector. So that's the definition. Okay, so these are things called connections. All right. Now E0 dot EA equal to 0 means if I take E0 dot this, I will get exactly this result, and so I will just find that E0 dot di EA is equal to this, and you can just show this very easily. Now EA dot EB equal to 0 means that gradient of EA has a piece coming along the direction of E0 and has some other connections, it has some components along the B direction. And because of all the properties that we have here, you will see that these connection objects have some interesting algebraic structure. They are anti-symmetric in A and B. Okay, with this background, we are ready to make the important statements. So if I take the derivative of the psi field remember is expanded in the EA basis, you will see that you can write this as di. So this is like some derivative in some space with a connection, EA and psi A, A0, E0. This is the result you get. Okay, with all of this worked out, we are actually ready to work out what is this derivative of ni, derivative in the I direction of the vector n. So you will see that if you just work through this, you will see that it has a piece along E0 and a piece along EA. All the work that we did was to make sure that we can write this derivative at a point in space in a naturally orthonormal basis. If you try to do this in some other basis, you will get a bunch of terms and then you will not know how to handle them. This one will allow you to naturally handle them. So when I take because E0 and EA are orthonormal, you see I just am able to immediately just find the magnitude of this vector, and it turns out to be this. Okay. So now you can see that this is highly nonlinear, right? So for example, there is a square root of 1 minus psi square, that's already very nonlinear and so on. So what we are now going to do is we are going to make two approximations. One is I am going to keep this only up to quadratic order in little psi, this fluctuation about the sigma 0, about the sigma direction, or the short wavelength fluctuations. I will keep the theory only up to quadratic order in those. The next approximation I am going to make is, so these are the terms that are valid to quadratic order. anytime I see something that is a product of a highly fluctuating thing with something that is long distance, varying on long distances, I will simply drop it, because when I integrate out, the fluctuations will actually average out to 0. So I can drop this. So the bottom line is I will end up getting this as the gradient n square. So remember, it has all this a0 and all of these terms, and all of them are up to quadratic order inside. One more final approximation can be made. This will take some work to show it formally, but you can at least see it intuitively. So for very small fluctuations about a fully ordered state, for example, you will be able to show that these terms are very small, they contribute some small terms. Therefore, this di can be replaced by simply the derivative. So with all these developments, and observing that A0IA is di sigma, sigma remember is our slow field, unit vector slow field, in the direction A in the local basis, you can rewrite this entire thing as this nonlinear field, because these are unit vectors, interacting with the up to quadratic order in some fluctuating fast wavelength fields, that is short wavelength fluctuations, and this theory for these fluctuations is quadratic. So it is a Gaussian theory. And now it is very simple for us to integrate out the psi a fields. This by now should be a straightforward exercise, and I would strongly encourage you to do it. And when you do this, when you integrate out this theory, you will see that there is a d sigma here. So when I integrate this out, I will sort of square this whole thing, and I will get a term which looks like gradient sigma square. This is sigma is a unit vector now, and you see the g that we had, it has this 1 by g, the dimensional 1 by g has changed to this. So this is the effect of the short wavelength fluctuations, namely the size, on my sigmas, which are the long wavelength guys. So I have done my integration part now, and I have got an effective action for the shorter wavelength modes. Okay. Now, when we next step is to rescale and renormalize. Renormalization here is nothing, because I have already chosen the unit vector, and all I have to do is to define the new n field based on the scale transformation of the coordinates, and that is just done straightforward here. So you will see that all that we have done here is just to replace sigma by n nu, and okay, I have not made the, I have not been very careful about, I should have called this x nu as well, but you get the drift, because these are the new coordinates, etc. And most importantly, the cutoff of this theory is restored back to lambda. So we can compare this theory with the theory that we start off with. So in particular, we have got the renormalization group transformation for the 1 by g coupling constant. So Rs of 1 by g goes as s to the d minus 1 by g times this something that depends on the symmetry and something that depends on the spatial dimension. CD is our usual SD, which is the surface area of a d-dimensional sphere, divided by 2 pi to the power d, and SD minus 1 is what we get from the cutoff calculation, that's by integrating out the high modes. So now I can find out what is the renormalization group flow equation. So I just convert this Rs into a differential equation, and that differential equation goes like this: dg by dl is minus d by 2g times this. Now there is no surprise in this term, because this is the tree level term, and this is what is called as one loop level. So we integrate out one set of short wavelength modes, and it is called one loop level. So it is a one loop correction to this g. Okay, so we have pulled off what is the RG flow equation for this. So now you see there is a very nice thing that happens here, just like we did for the Wilson-Fisher fixed point. we now see that if you think in terms of that spatial dimension as parameterized by 2 plus epsilon, we can start seeing the physics for different n's in dimensions greater than 2. So what do we see here? When n is equal to 1, we have the Ising model. When n equal to 2, we have the xy model. And when n is equal to 3, we have the Heisenberg model, model of spins, classical Heisenberg model. So renormalization group flow in d equal to 2 plus epsilon looks like this. And if I ask what are the fixed points of this, you will see that there is a nice fixed point whenever n is greater than 3. So G star 0 is always a fixed point, that is our 0 temperature broken symmetry phase. For Ising and xy, there are no new fixed points. In fact, you will find that for Ising, this will still give me an irrelevant operator, because you see n equal to 1 means this will be minus G square. So this is still irrelevant. So at this order perturbation theory or at this order of at the one loop level, I am not able to destabilize the 0 temperature broken symmetry phase. It is very stable if you wish. If I am xy, then again I don't, it is an irrelevant operator, which means I can have an xy ordered ground state, that is O2 symmetry broken ground state in d plus epsilon, and perturbation to order G square do not destabilize it. There is nothing that that will slow down the irrelevant flow back towards the fixed point. But when n is greater than or equal to 3, that means the symmetry is at least as much as the Heisenberg spins, then we see that there is actually a fixed point at finite positive G, which is order epsilon. In fact, you can I call it the Heisenberg fixed point, and you can just calculate it just by equating it to 0, very straightforward. You will see that it goes as 1 by CD to the n minus 2 times epsilon. So what happens is, for n greater than or equal to 3, you find this Heisenberg fixed point. So you have found the TC of the Heisenberg model, if you wish, in some epsilon expansion, epsilon now being d plus epsilon. Most interestingly, we know that this is a critical point. Why? Because if I look at the flow near this critical point, you will see that G is an unstable direction, which means it is a critical point. So this is a phase, and whatever, when it goes to infinity, that will also be the paramagnetic phase, and this broken symmetry, ON broken symmetry phase is separated from the paramagnetic phase by this critical point. Okay. So you can actually compute all the interesting properties. So G here, remember, is like temperature, so you can compute what is mu T or mu G, and you will find that that is equal to epsilon, and from there you can actually calculate all the critical properties the way we have done in the past, in the last lecture particularly. So you can extract the critical properties of the 3-dimensional Heisenberg model from this. It will certainly give you something qualitatively correct. It will be slightly off from the quantitative mark, but that's to be expected, because you have to then do more loop terms and so on, and sum the series and all of that stuff. But this is remarkably encouraging, because we have now got access to d equal to 3 through the sort of the broken symmetry side of d equal to 3. Very good. What happens in d equal to 2? In d equal to 2, first of all, in d equal to 1, G is relevant, so we do not even care about the cubic, the one loop term, because okay, it will do something, but it will push, you will be pushed out of the broken symmetry phase and you will go into something else. In d equal to 2, G is marginal at tree level, which means that the theory has nothing to say about, it says that at tree level you do not destabilize the broken symmetry phase. But if you think about this a little bit more, you will see that in d equal to 2 there are 3 cases. The first case is the Ising case, where n is equal to 1. And now you see something very interesting. G is marginally irrelevant. suggesting that the broken symmetry state is stable in D equal to 2 when n equal to 1. But this we know is absolutely true because we have solved the Ising model in 2 dimensions, classical Ising model in 2 dimensions exactly, and we know that there is a broken symmetry phase at low temperatures, and this nonlinear sigma model is actually pointing us to the fact that there is indeed a broken symmetry phase and it is stable. Now let me jump to n greater than or equal to 3. I started off with n equal to 1, now I am going to n greater than or equal to 3. And now you see something spectacular. n minus 2 is a positive number, epsilon is 0. So you see dg by dl is cdg square. So what is that telling you? That is telling you that this is a relevant operator and it will flow away. It will flow off to g larger and larger. Okay. So what is this telling you? It tells you that the broken symmetry phase at 0 temperature is not stable when you turn g away from 0, and that is the Mermin-Wagner theorem. It tells you that you cannot have a broken symmetry phase, and it will actually, since it is going to flow away, it will go to finite g, it will get a finite correlation length and so on. So it's going to flow away and it's going to destroy this order. So this is how Mermin-Wagner theorem fits into the renormalization group flow. Okay, I must also mention that this problem in D equal to 2, this kind of RG flow, see, when we in statistical physics and condensed matter physics, when we study RG, we are always interested in the low energy properties. So our RG flow goes towards infrared. Now in field theory, for many practical reasons, they are interested in understanding the flow in the other direction. What happens when you go to UV? So that's like saying that I am increasing my cutoff rather than decreasing it. So we are decreasing the cutoff. So if the question is what happens if you increase the cutoff? So they have something called the Callan-Symanzik equation, which we have mentioned in the past. So it tells me that if I increase the cutoff, all I have to do is to change the sign of the beta function because I am going in the other direction. So it becomes minus n minus 2. So now when I am going towards higher energies, you will start seeing that the coupling constant will fall. In fact, as I go to infinite energies, the coupling constant will go to 0, which means you see I will have gapless excitations. If G is 0, the theory will have gapless excitations and so on. So it looks like a free theory at lambda going to infinity. So this is an example of what is called as asymptotic freedom, right? So you know about if you have studied high energy physics, elementary high energy physics, you know about strong interactions and asymptotic freedom associated with that, etc. So this is quite, that's a little bit more complicated story, but conceptually this is sort of thing that is behind the asymptotic freedom. And now finally we are faced with 2 spatial dimensions and n is equal to 2. What do we find? The RG flow tells us epsilon is 0 and n is 2, so this is also 0. So you find that it is marginal also at the loop level. So what do we do? I mean, we don't have, how do we study the O2 model or XY model or U1 model in D equal to 2? What physics does that contain? Okay, so with that question, I will summarize this lecture. So sigma models can be used to describe broken symmetry phases with Goldstone modes, we have seen that, and renormalization group analysis reveals stable broken symmetry state at low temperatures in D is equal to 2 plus epsilon, and for n greater than or equal to 3, it reveals a finite temperature critical point. It shows that the broken symmetry state is unstable in D equal to, sorry, this is a typo, this is D equal to 2, not D equal to 3, this is D equal to 2 when n is greater than or equal to 3, and this is the Mermin-Wagner theorem. Okay, so I should also take a few minutes to tell you how important nonlinear sigma models have been in various areas of physics. So, they have appeared prominently in many areas of physics. So, let me start by a very interesting puzzle that was there in spin chains. So, suppose I take an antiferromagnetic quantum spin chain in one dimension. So, the symmetry is like O3 symmetry implemented on the quantum system. If I do the D correspondence, so it's 1 will be corresponding to classical problem in 2 dimensions, that problem will map to the nonlinear sigma model problem of the classical O3 model in D equal to 2. But we know that the classical model in D equal to 2 is gapped, because RG flow will take it to this gapped phase as we saw. That will allow you to conclude that the quantum problem, namely O3 symmetric quantum Heisenberg chain in one dimension, will be gapped. However, there was enough evidence that spin half chains are gapless. In fact, it can be solved analytically, and spin 1 chains are gapped. So, this is very strange. The O3 sigma model can be applied to spin half and spin 1 equally well, but one is gapped and one is gapless. So, this led to an extremely important concept called the addition of topological terms to sigma models. So, in addition to the sigma model action of 1 by 2g gradient square integrated over space, you can add terms to the sigma model which will turn out to be purely imaginary terms that will measure some kind of invariant associated with the field configuration, and this is called a topological term because it does not depend on the any particular configuration in detail about how it is varying. It measures some kind of global winding of some sort, and different spin configurations will fall into different classes of such windings, and what you do is you add a term that measures this winding. And Haldane was able to point out that when it is odd spins or odd half integer spins I should say, you will see that the topological term will have a very different effect than when they are even, that is integer spins. When they are integer spins, this topological term has no effect and it is same as the classical sigma model, but when it is half integer spins like spin half, then you will see that topological term will have some very interesting things to say, and it changes the spectrum completely. So, this was a very important observation by Haldane, that topological terms can change the structure of the spectrum. So, this idea has been used in, for example, understanding Anderson localization. So, Anderson localization is when you put disorder fermions are moving in some disordered background, then they can get localized. Their wave functions can get localized in space. That physics can be described by nonlinear sigma models. In fact, nonlinear sigma models with such nonlinear sigma models associated with Anderson localization, including a topological term, can be used to describe symmetry protected topological phases. In fact, they turn out to be a very nice way of classifying free fermion topological phases. So, you can see that this nonlinear sigma models are very powerful. They can describe a variety of things, and it's definitely worth investing some time in studying and mastering them. What do we do next? So, you see, we left with this puzzle of what happens in D equal to 2 when n equal to 2. So, this is the xy or u1 model in 2 spatial dimensions. So, I am sure you will want to know more about that, and so I will see you in the next lecture. Thank you.